Hello, this is our third tutorial on a system Verilog, and we are going to start on language basics, that is data types. In system Verilog, basically data types are divided into the two categories, 4-state type and 2-state type. From 4-state, normally in a Verilog, 4-state types are supported. 4-state means, let us suppose this is a reg 31 down to 0 r. R is any object or a variable that is of type reg, and reg is a keyword that mostly we use in Verilog. R can support 4 type of values: 0, 1, x that means unknown, and z that means high impedance. In system Verilog, a new category of 2-state has been introduced. 2-state means, let us suppose B is of type bit and bit comes under the category of 2-state. Now B can support only two type of values, 0 and 1. What is the benefit of having a 2-state type? Execution time of 2-state type is much faster in comparison to your 4-state type. That is the one thing. 2 states, better performance, reduce the memory storage. What is the queue, dynamic associated array, that we cover later on. In Verilog we have only two type of data types, that is categorized as a net and reg, or called register. Net in Verilog includes wire, wand, var, etc. And register is further is of int or integer and reg. And it is sometimes becomes bit tough to understand whether to declare a variable as a reg type or a var type. So in system Verilog, a new data type has been introduced, that is a logic. You can say logic is a modified version of your reg. The old reg type has been extended to so it can be driven by a single driver. That is one thing. We're very much aware about the parameter keyword in Verilog. Size 64. Now instead of writing data as a 63 down to 0, you can write size -1 down to 0. You can initialize every bit of data that are 3 bits. If you have initialized with the 0, you can write 0 and data. If you want to initialize all the bits with the Z, then you can write tick B for stands for binary, and Z, and X for Z for high impedance, X for unknown. If you have to declare all the data bits as a 1, then you can go for 64, take H. This is the way you are following Verilog. Now system Verilog, you are not required to do like we did in a previous case. Just do data tick 0, data tick Z, data tick X, and data tick 1. This will fill all the bits with the X, all the bits with Z, and all the bits with 1. And this facility is not available in Verilog. Reg is replaced by logic, that we have discussed. Categorization of 4-state and 2 states. Logic comes under the category of your 4-state type. Bit, byte, short int, long int, they all come under the category of your 2-state. But your integer comes under the category of 4-state. And if you have to refer your byte is referred as a half word, content as a word, and the bit as a integer and int as a one long word, long int as a two long word. Okay, we will cover this enumeration later on. So whole and soul your categorization in this way, that is having a two data type is divided into two categories, 4-state type and 2-state type. 4-state includes logic, that means logic can support 0, 1, x, z. Rest bit unsigned 2-state type, signed 2-state type, that is int, byte, short and long int, unsigned form like this. Okay, the one is a void type, string type, all this, a lot of things that we will cover later on. String just to display some value. Okay, let us move on to a very strong thing of your system Verilog, that is the array. Arrays are categorized into two types: fixed array. So system Verilog includes two type of array: fixed array and dynamic array, and this facility is not available in Verilog. Fixed array is further divided into two categories: pack array or unpack. Now we will see what is a pack array and what is an unpack array. I think you're aware about what is an array. Array is a collection of variables all of the same type. Okay, now see how the arrays are different from another type of array in system Verilog. So what is the syntax? Int, that is a data type, and array1, name of array and size. This is your fixed size array. So fixed size will be given single dimension, and this is your single dimension. Okay, another way of writing of same, you can write int array to 5 down to 0. Both are same. This type of arrangement is called compact declaration, and this type of representation is called verbose declaration. Okay, so what is a packing and unpacking of array? Okay, so we'll go with this array representation. Understand what is an unpack array. Fixed type unpack array. By default, any unpack array is of 32 bit. One long word. This is your unpack array. Okay, with elements, 6 elements, and by default, all the unpack array is of size one long word. That is 32 bits. Now, what is this is also of 32 bits, but now what is happening? Array 1 with the 6 elements, and each element is of 32 bits. Like here, this example. Bit data type, like int is a data type, d1 to d2. Name of array. You can write 0 down to 7, 0 down to 23, or you can either write 8 and 24. Okay. Now what is happening here? Take this example. Array 3 element, right hand side. This representation is your unpack. This representation is your pack or vector size. Okay. Now we are having a one array of 3 elements: up array 0, up array 1, up array 2. Okay, and by default, up array is going, as it is unpack from the category of unpack, it is going to be of one long word, that is 32 bits. 8, 8, 8, and 8. That is 8 into 4, 32 bits. But what is actually happening here? We are utilizing only 8 bits of out of that 32 bits. Rest this space, that is 1 block, 2 block, and 3 block, of no use. This is your wastage. This is your wastage. This is your wastage. This is a problem with the unpacker. Let us see another example. This is fixed size unpacker. Again, same. If you are going to assign this thing, up array 0, tick 0. 8 bits that up array 0 element will be 0. About this up underscore array 1, tick 1. All the elements of up array 1 will be, all the bits of element 1 will be 1, and this thing. Now see, up array 2, 3, 1. So what is happening? You are targeting third element, sorry, second element of your up array, and third bit 0, 1, 2, and 3. Third bit will be 1. Okay. Now see, important thing I want to discuss that system Verilog is weakly typed language as VHDL is strongly typed. Now what is the benefit or what is the meaning of weakly type? Now see, you are defining a b underscore unpack 1 down to 3 array of 1, 2, and 3 elements, and each element is, as it is written on the right hand side of b underscore unpack, that means it is unpack array of 3 elements, and each element is going to consume 16 bits. So 16 bits. Okay, out of that 32 bits. Why 32 bits? Because it is an unpack array, and by default unpack array consumes one long word of the memory. Now you have started from 60 down to 1 and unpacked array 1 down to 3. So you are defining b underscore unpack 0th bit tick 0. So what is this? Is your out of bound. There is a no 0th bit. So instead of giving an error, simulator will skip this statement. That's the benefit of weakly type language. Rest we will cover in our lab session. Array 20. So you are having a 20 elements of array named as array, and each is of 32 bit long. and that is 0 to 19, and you can, this is your 60 down to 83. Okay, 60 down, not down, 60, 64 to 83, each of 32 bits, both are same, but here starting element will be array 64, here is the starting element will be array 0. Okay, now this is something important, and this is your multi-dimensional array. What is a pack array we will cover later on, what is a mix array we will cover later on. Okay, okay, this is your 2D array, and from the multi-dimensional array, that is 2D 3D, or you can go for as much long as according to your requirement. Now what is happening here, we have defined array 1 of 6 bits and each of type int, and it is going to be a long word. Okay, so how you can assign, how you can initialize that 6 bits. Okay, let's see what is happening. Here you are having array 1, take this curly brackets 0, 1, 2, 3, and 4 and 5. Now what is happening here, that is important to understand. 0 will be 0, and array, this means 2 bits. Why? Because this is your unpack array. Unpack array is 32 bit long, and this is again 32 bit long, 32 bit long, 32 bit, 32, 32, 32. Okay, now see, now we will justify that thing. What does it mean in our simulators? Okay, wait a moment for that. pwd present working directory. So now I don't want to work in a C. I have to change the CD to change the system error log under the files, new source, and system error. Okay, now give the name of module, any name, save with the name of module. Now here, keep one thing in mind, in the whole rest of our series I'll do everything with the initial, not the always, because this are codes and system are look for verification. When you're writing a test bench, you always go with the initial, not with the always. I think that is clear to you now. As always never terminates, it's keep on executing and wait for any activity that given in its sensitivity list, but initial block will execute every statement only once. Okay, more thing. No. Okay, notice one thing. I have declared array1 after I have declared array1 outside the initial block. Okay, and untick this enable optimization, because we don't want to do any optimization for this particular code, because it has nothing to do for the optimization. Okay, you have in simulation mode now. So this is your object window and this is your memory list. Okay, see, I have double click on this memory list. We are having a say 5 elements, and then this is a 1, 2, 3, 4, 5, and 6 elements are there, and each of 1, 2, 3, 4, 5, 6, 7, and 8, and each is, this is a representation in hexa. Okay, 8 into 4, 32 bits. Okay, this is H hexa. So you see here what is happening now at the back end of the memory. You have declared only a 6 element of array 1, 0 to 5 or 1 to 6. Okay, and by default, as I mentioned, it is an unpack array. Mm, so big. Uh, see, let's see if somehow I'm able to. Sorry. Hmm, Can I reset it? Somehow change column variability. No. So okay, so leave that thing. Array 0 is of 32 bits, and this is hexa represented specially given fixed array. The simulator is so smart that Quastasm that is going to capture everything by its own. It's a fixed array. It's showing you. Okay, then it might be uh, number of things are there. Okay, instead of doing that, we will make it pop up. Okay, see this thing. It is showing you everything. Kind, fixed size. Okay. So what I want to make you prove that all the unpack array, regardless of what is the size, are going to have is going to be one long word. You're going to take one long word of your memory. If you are using only 7 bits like we are doing here in our previous slide. Where's that? Yeah, see this one where we're utilizing only this. Look at here, vectors. We're utilizing only 16 elements of this particular array. 16 bits of this particular element of an array and b underscore unpack. So rest of 16 are unused. So this is a memory that is going to be waste. Okay. So this is a concept of all your fixed type of array, especially for pack array. Okay. So what is happening here now? See, this is the assignment operator. How to do the assignments now. Program is in simulation mode, and this statement is still not executed. Is not simulated. So rest all the elements are I'm getting 0 0 0 0 0. So how to do that? So you can go for the writing step. Click this thing, and this is see every element has been modified. So actually it is a hexa representation. If you open this thing, what is happening here? See, every bit is 0. See this, only one bit is, we are assigning only one this, rest of our key will be unused, like that. Okay, not unused, you're giving only one, so this is a representation 1. Similarly for 2, if you open this will be 1 0. Yeah, similarly for 3, that is 1 1. You can see this 4 1 0 0, and this is happening, this is 1, and the rest is a 5, that is 1 0 1, and this is 1 0 1. Okay, so this is a concept of your unpack fixed size array that going to consume a lot of memory. And you can go also utilize the dollar display statement to see what is actually happening in your command window. At the transcript window. This transcript window. Presently, we're observing everything at our object window. Okay. This is concept a bit complex, but you will be handy as you keep on doing all this uh, by taking all the example by your own. Now, if I have to quit simulation, you can go for here start, sorry, simulation and simulation, or you can write quit minus sim. That will also do the same work. Mm. Now, see how to insert dollar display. Dollar. Yes. If I write only we have this will not work. This will not work. Okay, but I just want to show what will be the output of this. Okay, let's see. There will be no any, and there will be not any syntax error. The syntax is correct. No. Everything is going nice. Look, it's not showing anything. Hold on, let's see. Okay, B, B, B for binary. Okay, nothing. So how can I have something like how can I make this dollar display work? Okay, let's do for that. Sorry, you have to add one here. I have to add one name. Look at here. Look at here. So this is the correct way. Percentage p will be included for unpack array. Okay, you have to take care of this thing. Now one last thing in this tutorial I want to share. If I do this declaration inside the initial block, even that is correct, but what will be the effect that we have to observe? Now see what is the effect of your object window is totally empty. If you declare anything inside your initial block, and that will not be global, that is only for this initial block, so you're not able to observe that thing in the object window. Okay, there is no error, no logical error, no syntax error, nothing, everything finds, everything works very fine. Like see, step step, you're getting a value of this everyone properly, but we are not able to see that thing in object window. But you see memory list, even that is totally working. We are getting updated everything in the memory, but there is nothing to see in object. Okay, that's all for this fixed size unpack array. In next tutorial we'll try to cover the fixed size pack array. Okay, thanks a lot.